All right, so let's continue the discussion on the Bayesian non-parametrics technique. So far, again, Bayesian non-parametrics, represents a set of technique that defines distribution over distributions, right? And previously, we also studied distribution over sets and the distributions over functions. Today's lecture is about another class of distributions which are also on distributions, but it's on the features that we use to describe data. So again, it has an interesting, culinary metaphor called the Indian buffet process, and we're going to see how it looks like. Just to recap, last time we covered the Dirichlet process. It can be used to provide a non-parametric Bayesian version of the finite mixture model, where you can cluster this data, colored in here, without pre-specifying the number of clusters. And then there is a process that allows you to instantiate, a new cluster when the data appears to be, requiring a new cluster to be instantiated. Okay. And more formally, the Dirichlet process can be derived from a infinite limit of Dirichlet distribution. If you remember, it basically can be, derived from like this by alpha over k. By taking this finite dimensional k-dimensional Dirichlet distribution, into infinity, and then it generates a distribution over the atoms, and the weights, are infinite dimension. Okay, and also, so this is where we actually draw pi from. The pi is known as a Dirichlet process distributed. And then we talked about a few other, expression of the same partition of the space, identical to the Dirichlet process, but more in the form of a predictive distribution, which is more in the form of, say, xi given x not I, right? And I hope you still remember what is a Paya-Erm process and what is a Chinese threshold process. It's all about how to determine the character of the sample at hand, given all the previous samples, right? And in this case, you only rely on the distribution or the labeling of the previous examples, say color of the balls or seating of the clients, but you don't actually use this pi anymore. There isn't a explicit vector parameter that you define, a assignment. And that's because this pi is integrated out. You have a marginal predictive distribution of a new sample, right? And from that, you actually see a new phenomenon, which is known as the rich gets richer predictive distribution, that larger clusters and larger peptides are more likely to collect new samples, right? So that's the second property. And then there are other ways of describing the distribution as a process, which if, for example, in this stick breaking process, you can use an iterative procedure to generate samples, and in that you actually have a ordering of the pies from large to small, which gives you a diminishing tail of the pi that you can truncate. So you can see the same distribution can be described by multiple different, seemingly different, processes, and that's actually, the interesting kind of aspects of these type of distributions, and they often can be used to inspire inference algorithms. So this is the recap from last lecture. Hope you still remember. And but there's a limitation, of the mixture model, which go with the distributed process type of prior. First is that the clusters are not overlapping in the following sense. You can only assign basically a point to one cluster, at least in terms of the generative process. Okay. In inference, you may get a distribution of the label over all possible assignments, but that's a posterior. But a priori, every sample belongs to one cluster. Okay, and therefore, you really cannot use this model to share features. For example, share centroids. Say a particular data point have multiple centroids, right? So this is not possible. And prototypes, one person, collecting, genetic aspects from multiple ancestors, that is not possible, in a cluster model, right? Well, we have, and these are typical applications where you may need to, enable or necessitate, facilitate such sharing of the clusters, which is not possible under this process. So here I have a few examples. For example, if you want to cluster images, what if the image has multiple objects? It has a dog, it has a car, and maybe sky and so forth. Then how do you classify that, right? So it's not a one label. Then, the actors in a social network obviously has multiple social groups. They may not just become, joining one group. Like myself, I joined the group of academia, but also, I could be an entrepreneur and I could be a family guy and so forth. Right? So again, you have multiple group assignments. Movies, may have different aspects of, genres and so forth. Right? So that creates a need where the distributed process isn't the best way to do it. Well, today we're going to talk about a new approach, which is again, a latent verbal model, which allow you to incorporate the so-called multiple latent features that can be shared. The most kind of classic and maybe canonical example is known as factor analysis, and this is the model of the factor analysis, which is very, very straightforward. It basically says that every example, X, is just a linear combination of latent features. Okay, literally a linear combination plus some noise. So linear algebraically, we can represent this in a matrix form, right? So say, for example, here's an A matrix, which is just the collection of all latent features. So in here, for example, I have the A matrix in here. And then there is also a W matrix. This W matrix is data point specific. This is data point 1. This is data point 2, and so forth, right? And it is k-dimensional. And the entries in this row is basically the weights of how you're combining the features. So for every example xi, for example, it will basically correspond to this wi, and the wi will be used to combine different features. Each feature is actually a row in this A matrix. We are going to make a linear combination of these rows and synthesize or generate a X plus some noise. Okay. Well, there are examples that you see before, which is say LDA, for example, is allowing you to combine different topics, right? But we didn't use this linear combination of topics because that will create a X that is continuous, right? And remember, in the LDA model, we are modeling text documents that are discrete. It's words, right? So therefore, we produced a hierarchical generative process that allow you to pick a topic and accordingly pick a word and so forth for every document and for every word. But in here, we're talking in a much more general setting of generic feature combination, and therefore this feature this factor analyzer is the canonical example we're going to keep using today. Okay. So so this model is finite, right? We have a finite number of latent features, and of course the samples are also finite. So can we imagine that we may have an infinite number of samples? I don't know, maybe many, maybe infinite. Before you see everything, you can only assume that. But can we also assume that the number of features in here is also a priori finite, infinite? So this is actually a question we'll ask, because in the Dirsch process, if you remember, we actually don't pre-specify the number of clusters, right? So here we ask the similar question: can we avoid specifying a priori the number of features? See? Okay, so that's basically the topic today. You can always see the value of that because it makes your modeling, practice a lot more flexible, expressive, right? All right. So there is a solution. The idea is that maybe we should, think about how to define a distribution over this matrix W, because if this matrix, can keep growing this way and growing, which accommodate more and more samples, and also growing that way, which keep getting us more and more features, then we actually could realize, an infinite feature model. And then, of course, as a result of that, this W matrix is actually infinite dimensional, right? It has infinite number of columns. And of course, the A matrix will have an infinite number of rows. So the problem becomes different now. We are now worried about modeling a different, infinite dimensional matrix. So that's a one jump of the task into a more explicit form. Okay, so how can we actually get a way to start? First of all, we cannot really analytically express an infinite matrix. There is no storage space that allows you to store that, right? In a sense, we only need to, we can only, basically assume the potential is infinite, but the actual data that you are going to work on, and also the actual number of features that is used, for those data are finite, but the potential is infinite, just like what we did in the Dirsch process. So how to enable that? And also, by the way, there are some other, biases. For example, this matrix needs to be reasonably sparse. That's almost like the natural characteristics of any, assignment or indicator or combination of synthesized function. Because if it is very dense, you fail to, really make distinction on different data points, and also make distinctions on different features. They basically are just doing the same thing. They all contribute or all no contribute. So these are some canonical or some conceptual preferences we may want to, incorporate into our model that we want to invent. So recall the Dirsch process. We spoke about a process known as the CRP. In fact, if you just think a bit more carefully, CRP actually does allow you to create an infinite dimensional matrix. But in this case, the matrix is known as the indicator matrix, right? Basically, it means that, say, suppose every row corresponds to a particular data point. Only it's a one hot vector. One of the entries is black, right? And all others is 0. And that basically creates a cluster effect that your data point, this client, for example, can only sit on one table. It cannot simultaneously sit on multiple tables. But it is a prior for a matrix. It's just a special matrix. What we want is a more generic matrix where every row has multiple non-zero entries. Right? In fact, they should not only just be 0 and 1, they should be any continuous number that you can use to perform a weighted combination, to produce examples in the factor analysis setting. So the thing we are going to do first is to deconvolve this weight matrix into two components. One is a Z matrix, which is a binary matrix that is sparse, which will tell you how to pick features, right? And then the other is a V matrix, which can be dense or it can be any real value, which is a repository for you to get the weights, by a dot product, an element-wise product with the Z indicator matrix. Okay. So how to, get a sparse or define a prior for a sparse, matrix Z. So here, I introduce a prior known as the Bernoulli beta prior. It goes like follows. For every K, every column in here, I'm going to sample a rate pi K from a beta distribution. Okay, there are a sequence of pi's. So basically, there will be a pi 1, a pi 2, a pi 3. These are just a unidimensional. It's a rate. It's a scalar. Okay, it is a number between 0 and 1. Let me write that. Pi K is a number between 0 and 1. Okay, and then you use this pi to define a Bernoulli distribution, a process where all the entries in every row of this. Remember this column in the Z correspond to among all the samples how this particular feature K is utilized. Okay, so it is utilized according to a Bernoulli distribution. It will be on and off. Okay, so in that way, I first go row and go column, and then go every row. I got a matrix of indicators. Okay. Is that sparse? And also how to define a distribution? Well, let's write down the distribution first. The distribution is actually quite easy. Okay, and here I wrote it down. Through just explicitly, bringing in all these, pre-specified distribution families that we have. One is this one is a beta, and this one is a Bernoulli, and they actually have analytical expressions which are after some and then of course I need to integrate out those pi's just to define a marginal distribution of only the Z matrix given hyperparameters. Hyperparameters are basically the rates in here. Okay, and of course there is a K, which is the number of features. In this case, let's first worry about a finite dimensional matrix with n examples. These are all finite. Okay. You can go home and work out. It takes some very well-known standard properties of the gamma function. Okay, after the integration, and you can write down a pretty clean expression like this. Okay, and here I introduce some shorthand for certain quantities. Mk is the number of occupants of a feature K by n examples. Okay, and this distribution is exchangeable. Okay, it means that it doesn't depend on the rows and the columns. And once you have this matrix, you can swap the row, you can swap the columns in the Z matrix. You will have the same, probability, because we write explicitly in here without regarding the ordering. Okay. So now you can probably, okay. By the way, are you always this yet? Okay. No more question. Maybe you should have one question, because I already originally promised that we should have a sparse, matrix in here. And how come this one is sparse? I don't know yet. Do we have a guarantee? Well, you actually could be a little bit more diligent and start writing down, basically write out these gamma expressions, and just look at how this whole equation look like. And here I did a little bit for you. Okay. Gamma function, if you know, if you recall, you can Google it from Wikipedia. It's just a sequence of multiplications, okay, of those numbers. And after expanding this whole thing, P of Z actually equals to a product of these numbers, okay, divided by n. Okay, and you can see that all these numbers are smaller than 1. Okay, and also once you have more and more k and more n, it tends to go smaller and smaller. Okay, and having more zero entry and more counts in the matrix will make the probability even smaller. Therefore, the higher probability configuration prefers a sparse matrix just by looking at this expression. Okay. So are we good? Is this one really a proper way of defining the distributions? Well, if we use this to draw, to define, a Z matrix, first of all, it's not really basically, have a lot of identifiability issue, because it is exchangeable over rows. Therefore, the same matrix with the rows swapped will have the same probability. Therefore, you have ambiguities in there. And also, there may be a lot of zero columns. You can definitely have possibilities of having empty columns in the middle, and that still needs to be modeled under this. So what we are going to do is to do a little bit more cleanup of the PZ, because Z is just a too ambiguous a matrix from a operational perspective. Okay, there may be columns which are identical, and there are empty columns and so forth. So we're going to focus more on another entity known as the equivalent class of Z, which does a little bit cleanup, known as the left ordering. Okay, left ordered binary matrix, which basically says that it's actually look like this. Instead of working on this matrix, you do some column and the row arrangements, so that you can make the the mass or the non-zero entries focusing more on the upper left side of the matrix. Okay, so that's basically just a reordering of the matrix. It's the same matrix. Okay, and we're going to now define basically multiple matrix in here. Maybe I should say m different matrix in here will get to one matrix in here. It basically can aggregate a lot of indicator matrix in here, which are essentially the same thing, into one expression, and we define now probability on this, which is a more concise and compact distribution. And this is usually not very, very difficult. You can introduce a few shorthands. For example, we define a history for every feature. So for example, now you are at say point n plus 1, okay, or maybe point n, let's say, and here we have all the way from n1 to n minus 1. Then we look at the feature k, and then this basically is your history vector. Okay, and with the history vector, you can define basically a count of that feature. so that you can keep track about how often this feature has already been used. Okay, and these numbers are useful in defining the total number of configurations, of the equivalent class. Okay, and or how many configurations a particular left ordered equivalent matrix can be represented when the order is disrupted, and that will help you to now define a probability distribution over that equivalent class. Okay, and it's actually quite simple because it is we know the exchangeability already. All the configurations belonging to the same equivalent class are equiprobable, and we know the total number of that already, right? So we're going to just multiply this number with the previous expression, which is the probability of one configurations in Z. Okay, so you arrive at this expression. Okay, so it looks very hairy, but that's the way it is. It's a distribution of the equivalent class of a Beta-Bernoulli generated binary matrix. Okay. Now it's time to play the trick of pushing for infinity. Remember that in our Dirichlet process, we have this, and then when k goes to infinity, we have a dp, right? And here, we start from a finite dimensional Beta-Bernoulli process, and now let's see when we take k to infinity, how things look like. Well, it's just some very standard algebraic interpretation manipulation, and we're going to get this expression, okay, as the infinite limit of that left order equivalent matrix. Okay, and this particular term actually is interesting. We're going to use it down the road because it actually implicates the total number of times, the expected number of times a feature is used, but we're going to talk about later. This number h is I'm going to talk about later. It's basically a sum exponent, a telescopic sum of that kind of, yeah. Okay. So any questions so far with our first exercise of defining a distribution over matrix, over infinite dimensional matrix? We have now a distribution over infinite dimensional matrix already in this case. Okay. And there's another number here, k plus, which means the number of features that is occupied so far. Okay. And what is kn? I think it is written somewhere. Yeah, kn is the number of features processing, a particular kh. What is kn? I need to check out. It's probably written somewhere. I forgot. I think the kn is the number of features used by sample n. Therefore, for every sample, you are going to have a k for that. Okay. All right. So remember our routine before. We define very formally, a Dirichlet process using the infinite limit of a Dirichlet distribution. And here we did the same. We used the infinite limit of a Beta-Bernoulli to define a distribution over infinite matrix. And then over there in DP, we marginalize out those rates for drawing examples and start to define a predictive distribution of the next sample given the previous samples using, a Chinese restaurant process, for example, using a culinary, metaphor. Interesting enough, here we can also use a culinary metaphor to define a predictive distribution, which is how do we do xi with x minus I. Okay. So here is how, for every data point, this guy represented by a patron, how he selects the features. In this case, the game is not about picking a table, but actually take what to eat. And here's a story. Imagine that there is a Indian buffet restaurant with potentially infinite number of dishes. Okay. If you guys go to Indian restaurant, you can see they are very different from the Chinese restaurant. It's not basically sitting you on a table first and bring you, the menu and pick dishes. In many cases, it will lead you to, a big long table with many delicious dishes out there, appearing to be infinite, and then you will be sampling based on your appetite, right? And maybe also based on how you look at other people pick their dishes. And this is the case in here. The first customer, because there is no other customers before yet, he's going to draw, from a Poisson distribution with rate alpha. Again, Poisson distribution defines, a distribution over discrete numbers. You may also Google the wiki and find out what that corresponds to. It tells you, how many number of letters you're going to receive every day, how many train stops, and how many cars passing by a traffic light if you stay there for long enough, and so forth. So these are the nature of this distribution. It basically depends on, it basically tells you the total counts of many independent events. Okay, each of them happen with a rate. So this guy will decide, a number and then pick the dish accordingly. Okay, then the later customer comes in, and he will basically do the following. He will first, look at the other customer's pick, and if he see a dish that is already picked by other customers n times, then he's going to sample that dish with this rate. Okay, m is the number of times that dish is used, and n is his ID, the total number of customers currently in the buffet restaurant. Okay, and that's not enough. He wants to try something new. Therefore, there is a new process, a new action, which allows him to sample some new dishes using a Poisson with a diminishing rate, alpha over n. N is the number of current customers. You can see that when the customer getting more and more, he is less and less likely to sample new dishes because there are already a lot many, being already tried by other customers, so that he can make an opinion about. So that's basically how it goes. And you can see this will result in also a random matrix, right? And in fact, the random matrix looks like this. You probably can see that there is also a left, ordering-ish kind of behavior in here, because the first customer, he would sample a few and put it in his plate, and the second one will use that one as a reference point and sample more. Therefore, you can see more draws are kind of taking place along this direction. But again, from time to time, there are new examples, new features being used. So you can also write down the probability of the Z produced using this manner. Okay, and in this case, we don't have a say a pi, for every feature. We don't have that, right, for the entire feature, and we also don't have what is that? Yeah, we don't have also a prior for you to draw the pie from at this point, right? But what we have are these examples, clients coming earlier, and also a global alpha, rate to define the Poisson distribution for the number of dishes. But still, you can write down, the probability of this entire distribution just by following up the process. This is basically that Poisson distribution for you to sample novel dishes, right? Starting from the first one all the way down to, the later ones. And then these are basically, our, reference process that I look at the other customers' dishes and sample accordingly, okay? So if you just work out this equation line by line, at the end of the day, you will arrive at this. If you still remember, our earlier exercise of the infinite limit, of that Beta-Bernoulli process, of the equivalent class of the Z distribution, you will identify that these two are identical. So that matrix can be sampled from an Indian buffet process, okay? And in the Indian buffet process, we have a Z given Z minus I, which is very, very similar to our CRP, where we have the clients given all the other clients, and the rates, are integrated out, okay? Okay. What is the property of the input process? Well, the property of the input process allows you, hopefully, just like in CRP, to see from a more kind of a localist perspective about a user experience, and also, some of the nice, aggregation of property. For example, this rich gets richer property now become very, very obvious that popular dishes will be more likely to be picked. In here, the dishes correspond to a feature that a consumer can use. And also here, remember, the consumer can pick multiple features, multiple dishes. This is very different from the Chinese restaurant process, where once you sit at a table, you cannot sit on other tables anymore, right? And also, there are some important properties that you can show, you can prove using, properties of the Poisson. Okay, for example, the number of non-zero entries in each row actually is a Poisson distributed, random number because of the exchangeability, and also the number of non-zero entries, of the whole matrix is also distributed, with a Poisson rate of n times alpha, because now you have n rows, not just one row, right? And you also know that the Poisson variables are additive, and according to their rates. And so these are nice properties of the Poisson distribution. You actually can also show that the number of the total number of non-empty columns, okay, which is really the distribution of the number of features being used, can also be analytically expressed, okay, as a Poisson distribution. Okay, so now we have a Z matrix whose distribution is properly explicitly known, and also can be realized through a sampling process, and also it is infinite dimensional. How can we actually start to use them to model real data? Okay. Remember, in the Chinese restaurant process or dietary process, we basically are really, drawing, we're basically drawing a class label for, this particular example. Let's say we call them ZI, which sits you on a particular table. And then you need to start defining a likelihood function for the data, right? So which is to allow them to be clustered. For example, at the end of the day, this likelihood of the P of xi, has to be defined by, a mu of zi equals to k, so that it is assigned to cluster k. So k basic, this mu is the parameters, almost like the dishes sitting on the table in the Chinese restaurant. So that's how a real data point can be associated, with a atom, in a diffusion process, which basically just defines, the probability of a cluster. So in here, just having z is not enough. It's just to indicate which feature to use, but it does not yet fully specify the likelihood of a real data, which make use of the feature and also have noise on top of the features, right? So, for example, this model. So how to make that happen? The simplest approach is called a linear Gaussian model. We're going to now, draw entries of the A from a Gaussian distribution. Basically, we are saying the features, every feature K is a Gaussian distributed vector or a scalar. And then we're going to, use the Z or the W to make a linear combination. So if here we say W equals to Z, then the W is a binary matrix of black and white entries, right? And then you are going to get something like this, right? Say these are 4 features with all different shapes. And then for particular sample I, I have this particular row of third, second, and third, and fifth to be 1, others in 0. Then I pretty much picked this one, and that one. Oh no, this one, and not this one. And that's how the whole thing look like. It's a triangular, superimposed on a circle, and then superimposed by another bar like this. Right? And then you may add a little bit noise on that. There is no trace of the square and the star the star in here, because they are set to be 0. Okay? So that's a property of the linear Gaussian model. If you like it, you will be able to use it. Well, people very often don't like it because this linear Gaussian model is really, a all or nothing model. You can only pick a feature, as it is, or you just kill it with a 0 weight, right? And therefore, this is a binary loading matrix, which sometimes disallow, flexibility. Sometimes, the features may carry different weights, and this is disallowed in here. So then, we could go back to our original idea. We want the Z, the W, not to be just a indicator matrix, but a weight matrix. Okay, and we use the IRB, the input IBR, to generate the Z indicator matrix. But then we use a element-wise product operation to pick the real weights from a random real number matrix to produce the W. Okay, so that basically is a 3-step generation process. You need to have the Z from IBP. You have the random matrix V from say a Gaussian distribution, and then you need to have the feature matrix also from a Gaussian distribution. Okay. All right. So these are just the principles. Maybe we can work an example to see how people use it to model real data. So here is an example came from Frank Wood, who is a professor in UK, Oxford, and he was one of the early practitioners of and also analyzer of the IBP. So he used this model to come up with a patient diagnostic algorithm. And here is the problem, how it look like. Your data point will be patients, and your observation from patients will be the symptoms, say having a fever, cough, and so on and so forth, a number of them. And then your goal is to identify the biologically plausible latent causes, which could be like a illness. So for example, common flu or COVID-19 or pneumonia or whatever, okay? And all these may generate some similar features and some different features. Now you are so probably well educated about COVID-19. You know that in COVID-19 we have some symptoms which are cough and breathe difficulties and all that, but not necessarily fever and running nose. And the common cold also have cough, may also have, well, maybe not so badly on chest or breathing problem, but they have a, fever, running nose, and so forth. So different diseases share some symptoms and have their different symptoms. So how to model that for an individual? So the idea here is that you want to have each latent features to be associated with a set of symptoms, just like what I just said, right? Each disease have multiple symptoms, and then a patient will display some symptoms, and if he displays symptoms that are really if these features or multiple features is really associated with the patients, then the shared symptoms are likely to be discovered. So here is the modeling process. Again, very, very mechanical. Down the road, you can use this. Again, this is a graphical model, right? You have the Z, you have X, and you have also, say, the Y, which help you to select some configuration, and you have the Z. And here is how they select. First of all, this is a Z matrix, which is we may call it a patient and illness matrix, which is of course unknown, which is something you want to uncover, right? So it's basically saying that for every patient, I have a array of potential illness he may have, and then this Y vector, which is defined on every observed symptom for every latent disease, is basically it's like a switcher, or a switcher which defines whether a particular disease K picks up symptom D. Okay, and then for a patient, a number N for symptom D. If this patient exhibits symptom D, then the likelihood of that is defined by this expression, which basically correspond to the following reasoning. This patient has an array of latent diseases indicated by Z, and then this Y is translating the disease into symptoms. Okay, and this is again a random variable. The symptoms is is showing up or turning up and off, depending on a Bernoulli process, depending also on the patients on the disease, and then whether that symptom show up in a patient is also a coin tossing. Okay, and to be on or not, and then there are some noises as well to see this, to further allowing uncertainties. Okay. So you can imagine that the multiple coins are tossed, in different stages. Here is a coin tossing, here is a coin tossing, and here is one. And then finally, you get your symptoms, unfortunately, with all this randomness. And then the whole point, the whole problem goes back to do posterior inferences of the Z, and maybe sometimes even Y. Okay. So that goes to the inference problem. How can we infer? the ending buffet process. And as we recall, in the division process, we have a number of approaches. In fact, I didn't discuss a lot, in the lecture. It's too technical and too tedious to go through all that. But the papers we posted on the website gives you a lot of details that you can go. It range all the way from Gibbs sampler, based on the exchangeable model, which is the CRPs, or you can directly sample from the underlying distribution, just as using the stick breaking process and so on. It could also be a variational inference that you do truncation and then set them into finite. And there are particle filters using important weighted sampling technique and so forth. We can use similar ideas to construct analogous samplers for IBP. Okay. First of all, a very important property is this exchangeability, meaning that the rows, the ordering of the rows and the columns in the Z matrix isn't going to change, the joint probability of the whole thing. Okay. Therefore, you can always, treat any one or column in that matrix as the last row and column in the matrix, and setting everything else to be, the predecessor. And that gives you, the context to apply the IBP. Remember, the IBP basically describes the behavior of the last customer giving all the previous customers, and that's exactly what we can use here. Right. But also here, we're not going to be only sampling a matrix of indicators. We have real data, which is the X, meaning that I observe the incarnation of the features, on real world. That means the noises are also integrated, are also present, in those examples. Therefore, from the feature that you've chosen to the actual observations, you actually observe on sample, there need to be a likelihood function, which is actually this F function. You define the likelihood, okay, of the sample, given how the features are chosen using the Z, and also this likelihood function parameters, such as a Gaussian model or some other models that you like. If you have a novel kind of sample, a feature to be used, which is not present in the history, then you need to, basically use, another, formula which gives you, the likelihood of the sample under a new feature, and also this is the rate to go to the new features. So I'm not going to walk through the details. It's very, very tedious, but the idea pretty much, is analogous, maybe even in parallel to what we see in the division process. Okay. Oh yeah, actually, here I'm not talking about new yet. It's just about using or not using the feature. But if you want to actually, add new features into that, you actually need to go through yet another, step, which needs you to compute, first of all, the probability of sampling the new features, which we know follows a diminishing, Poisson distribution, and also the likelihood of the sample under these new features with their, weights integrated out in a fully Bayesian manner. Therefore, you have this, likelihood ratio to help you defining a metropolis Hastings step, together with the likelihood of function and also, the new Poisson rate. And then we can determine whether this new step of instantiating new features should be accepted or not. So all these are very mechanical, even though very complicated and very heavy, but it's mechanical. You can just plug in every steps and see how it goes. Okay, any questions so far? I have another 20 minutes, and I plan to use that to dive a little bit more into some of the theoretical aspects, of the input process to see what is the, the kind of fundamental stories behind all these, generative processes. But before I dive there, I want to take a few minutes to answer any questions from you. You can either raise your hand and ask, or you can type. Somehow I couldn't see the chat window. Where is it? Any questions? Oh yeah, I brought up the chat window. No, I didn't see it. Yeah. Anyway, somehow I couldn't find the chat box, on Zoom from my screen. If you have questions, just either raise your hand or directly unmute and shout out. Otherwise, I'm going to move forward. Okay, let me just move forward then. Recall that in our presentation of the Dirichlet process and the Chinese distribution process, the DP is really defining a prior over the probability measures, which we call atoms, right? But the CRP is not actually defined on those measures. They are directly generating a partition, and all these random measures, which is the probability of every cluster, is integrated out already, right? So in a sense, this CRP and DP are the two sides of the coin, which exhibits or expose different characteristics of the same distribution. And using the definite theory, we know that if a couple of all these sequence of examples, so the customers are exchangeable, in terms of their influence on the final joint distribution or partitions, then there must exist a measure condition which these are IID, which is the Dirichlet process. In this case, it is the DP that is integrated out. So you can see this IID and this exchangeability, is not contradicting each other. Okay, in here it looks like the sequence of X are not IID because they, are basically, dependent, on one and the other, even though the order isn't matter. But if you have the DP introduced, then all these examples actually are IID. Right? So remember that if you use a graphical model, if we have a DP and we draw all these Xi, then they are IID. But if the DP is integrated out, then in our elimination mechanism in graphical model, all these become interdependent of each other, right? Even though they are exchangeable. So that's very, very clear for Dirichlet process. Now we ask in IBP, which is the IBP is more like a CRP, right? It is really defining, a exchangeable process and distribution, on sample directly. Is there an equivalent version of DP in the underlying the IRB? Okay, so that's basically a question. Well, the truth is that there is. Okay, recall that we have the Beta-Bernoulli process, which we begin with, to sample the Z matrix. At that time, it was said to be finite. Well, these are beta parameters or beta variables, and then we use the beta variables to sample the indicators. So this process is known as a beta process. Okay. And the beta process are also generating atoms in here, just like the Dirge process also generates atoms, which is a vector of time. Right? Here, the atoms, are just a scalar with a mass between 0 and 1. So that's basically a counterpart of DP in our IDP. And then, remember in the DP alpha, and once we have, plus some data sets, we can actually also write down a posterior, of the DP of the atoms, of the pi, given DP, and also the example as also a DP with somehow reweighted alphas. I forgot the exact expression, but it's reweighted by the counts, right? That's basically making the distribution process a very nice prior distribution because it is conjugate. Your prior and your posterior look the same. So in our IBP, we know the prior is a beta process. How about the posterior distribution? It turns out that our posterior distribution can also be derived in closed form. Okay. Remember that in the beta process, we basically are really drawing atoms from a infinitesimal limit of a beta distribution of random variables, right? And the counts of the observation, which in this case, observations are the z, right? And the counts of all the z's that equals to 1 actually can be written as a binomial distribution. There's a theorem actually showing you that is the case because the summation of a finite number of Bernoulli distributed random variables is known as a binomial distribution, and here the Bernoulli rates are defined by the beta distribution. Right? So in a sense, if we look at the counts, we are going to see a Bernoulli or a binomial distribution. Okay. And then it is well known that binomial and beta are a pair of conjugate priors, conjugate distributions. Okay, and now we can go back and and write down basically a posterior of the rates given the counts. Okay, and given the original beta prior, okay. Okay, remember this counts is following a binomial, and this one is a beta, and the beta and binomial are just like a Dirichlet and the multinomial. Okay, it's conjugate. Therefore, the posterior is also a beta with race-scaled parameters. Okay, so this can be easily proven. Okay, that answers the first question. It is IBP is equivalent to a beta process, and the beta process is a conjugate prior for random measures of the Z matrix sampling rate, and the posterior is also a beta process, okay, with different rates. There's another equivalence that is also very interesting. In this process, we mentioned about a stick breaking process, okay, to allow you draw samples of the rates, and then that defines the atom and also the location, of the atoms. And without going too much into the details for the interest of time, here we have also a dual-shift process, a stick breaking construction for the beta process. You can read the text, but what is the interesting contrast is that in the DP, we break the stick from here, and then here, and then here, and we basically are breaking the remaining ones. Okay, therefore, the whole thing adds up to 1. Okay. So in the beta process, we have a very strange way of breaking the stick. You start from a unit stick, you break in here, and then you break it here again. You keep breaking, you know, you know, you keep throwing away, you know, the other part, and keep breaking what is, you know, state with you, and make it smaller and smaller. Okay, therefore, here we have this, and over there we have a multiplication of 1 minus mu. That's the difference. Okay. So all these tricks, you know, it's good to know because they will help you to design good sampling process for the inference. But if you just want to know the concept, you know, of the IBP, these one are less relevant. We're going to skip the inference part and maybe talk about a few more extensions. So when the IBP gets published, it generates a huge amount of interest in the community because it's a very, very nice tool to make flexible modeling of random matrix for combining features. But also people start to exploit, you know, stronger properties, you know, using the process without even worry about too much of the statistical details. So look, this is the vanilla IBP, which rely on a single parameter alpha. Okay, this single parameter alpha controls everything. It controls the expected number of columns to be used, the expected occupants of the columns, you know, for each one and for all. And having one hyperparameter controlling all this sometimes make people feel a little bit inflexible. Therefore, someone, in fact, this guy wrote a paper and introduced, you know, a new data, you know, a 2-parameter extension, which has beta and alpha. It looks like this. The idea remains the same. It's just the beta are differently parameterized. So as a result, this 2-parameter process allows some more flexible definitions. Okay, for example, here in terms of a realization, the process defines the following 2-parameter Indian buffet process. The first guy walks in and still gets Poisson alpha number of dishes. Then the later customers, when they pick clients dishes, instead of mk over n, they use m over beta plus n minus 1. Okay, the beta is helping to kind of damp or reduce the probability of a older dish being picked. Okay, they discourage basically reusing older features, and then they increase, you know, the probability of trying new dishes or new features. Originally, I forgot, it was alpha over n, something like that. But now it's like alpha times beta over this, which I believe is bigger than originally. Okay. And with that, you can also compute, you know, what's the global statistic. For example, here, it turns out that the number of features per data points are still marginally a Poisson for every row in the Z matrix, but the number of non-empty columns, okay, which basically is the number of features being used, are not only just you know, our earlier numbers, okay, alpha times a telescopic sum of some number. Here we have a different summation, which is making the number bigger, okay. And if beta sets to 1, then recovers the Poisson, the IBP process. So just to give you a kind of a sense about how the resultant matrix looks like, this is the 2-parameter IBP. This is the 1-parameter original IBP. You can see that now more and more features are being utilized and the matrix becomes sparser. So this is just a human taste. Some people feel that I don't want to overuse a small subset of features, but I want to really make a use of many more features. Maybe their data are just too noisy and too diverse, which necessitates this kind of practice. Okay. So that's how we augment the IBP for more flexible capability. There are some other, ideas to further extend the distribution of not just the random binary matrix, but just random matrix in general. Okay, the matrix could be, not just sparse and 0, 1, but could be dense and also could be real counts. You want to use the number of features multiple times and so forth. So these are all these other needs, and they can construct basically slightly more complicated distributions over that using still the IBP ideas. Well, let me just show you an example for closing, unless you have questions at this point. I have 5 minutes left. Yeah, so this is another interesting process known as the infinite Gamma-Poisson process. Okay, originally it's called the Beta-Bernoulli process. Now it's the Gamma-Poisson process. Basically, what happens is that we're going to sample a real number from a gamma and use it to scale the Dirge process. This is the analytical expression, but from a pragmatic manner, you can see, it creates something like this. You can associate basically every atom, okay, with a gamma process. Basically, we sample a gamma. And for every column, in that matrix, remember in the previous IBP, we basically associate with a column with a beta atom, right? Which basically defines a Bernoulli, and you basically draw a 1 or 0 from it. Now with a gamma atom, you basically can use it to define a Poisson, and then the entries, inside this matrix are no longer, a binary number, but a real number like this. Okay, so this is known as the infinite Gamma-Poisson process, and there are some good, properties in this matrix, which is discussed in this paper. It basically allows you to have better interpretability and control over how the features are used on real data. And so this is how it really looks like. At the end of the day, you basically, could use, again, a very, intuitive sampling process like what we have in IBP, to fill in this matrix. This is what we have here is the equivalent of the beta and the Bernoulli that allow to generate the whole matrix. But in translating to the IBP metaphor, how can we generate the left, focused equivalent class using, a conditional of every sample given the previous one? Then the Gamma-Poisson process actually translates to this. Okay, we are going to use now a negative binomial, okay, to sample existing dishes, okay, like this. And then you are going to use another negative binomial, to sample the new dishes. Let's say k equals to 4. And then these new dishes are actually distributed very interestingly, not put into one of these slots, but into all these slots using something known as the CRP, okay, which gives you, a way of partitioning, the features among, different, client, among different options that one client may have. The story becomes more complicated. It's less intuitive now. Basically, it means that this particular new sample not only will be picking up new features, in this way based on the early history, but also he will picking, altogether simultaneously multiple new features, okay, not just one but multiple, and then distribute them among the new entries using a CRP metaphor where some features are used more, some features are used less. So I have very little knowledge about the intuitions behind why this is good, but it is mathematically possible using the infinite Gamma-Poisson process. So with that, I'm going to close the section of non-parametric Bayesian models. It's technically slightly more intricate and complex technique, as you can see, in our graphic model class. But again, you can, hopefully appreciate, its capability in making the model more flexible, and also it's a building block in the bigger picture graphic model literature, for upgrading or extending existing models. We actually see applications of, for example, DP together with HMM to make the hidden Markov model infinite dimensional. You have infinite hidden states, even though you have a finite time series. We also see applications of IBP, in latent clustering applications and so forth. So if you're interested, you can look into some of these papers. So with that, I'm going to close today. By the way, you will be receiving some new notifications from Piazza and from email, hopefully, on our final plan for the class projects and the presentations. We understand that there are some disruptions now due to the online, arrangement of this class. We'll give you some more time to prep the final reports and the presentation, and also make the whole experience hopefully simpler, than what we originally hoped for, in the poster session. Any questions from the class before I officially close? Okay, no questions. Then thank you very much. I will see you again next Monday.